All right, here's a video of a worksheet that I passed out last week that we didn't get to completely go through, and I wanted to make sure you guys had all the right answers and explanations as to why. So if you need to review this at all, this is going to be your opportunity to do so. We also went through it really fast on Friday, so if you need extra help, this video should help you kind of figure out where I got those answers from. So on Model 1, it's giving us a picture of a penny, and it has different copper isotopes that are in the penny. And so question 1, does the sample contain identical atoms of copper? You should have said no. All right, it does not. If you look at the picture closely, you have copper 63 and you also have copper 65. So there's not identical atoms of copper. And so question 2, use the picture above to determine the percent of copper 63 in the sample. What's the percent of copper 65? And so basically what we're going to do is we are going to count all the copper 63 atoms and then all the copper 65 atoms. So I'm going to go ahead and count. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have 14, and this is going to be copper 63. And we have 1, 2, 3, 4, 5, 6 copper 65. And in order to find the percent of them, all we're going to do is divide the part by the whole. And so if you go 14 plus 6, that's 20. So 14 divided by 20, and if you multiply it by 100%, which I'm not going to add that, but you have to multiply it by 100 to turn it into a percent, you should get 70%. Okay, and if we divide 6 divided by 20, you multiply it by 100, you should get 30%. All right, now let's go ahead and see if we can find the average atomic mass of copper on the periodic table. And if you look at your periodic table, you're going to have it close to 63.546. Again, depending on which periodic table you look at, this could be slightly different, but it's somewhere around there. And part B, is it closer to 63 or 65? Well, it's 63.546. So it's going to be closer to 63 AMU. Now, how does this information from the picture above explain the answer to the previous question? Well, first off, you have to look. We have our 63 and our 65, and which one is more abundant? Well, copper 63 is 70%, while copper 65 is only 30%. So does it make sense that the average atomic mass is closer to 63? And it should say yes, it makes sense, because 63, so copper 63 is more abundant. Okay, so 70% of the time you're going to have copper 63. So it makes sense that the average atomic mass is going to be closer to that number. All right, page 2, question number 4. It says, consider the data table given in the table below. Determine the average mass of an element based on the data table of isotopic abundance and the mass of each isotope. So what we're going to do is we are going to use these numbers right here, and we have to convert these numbers into decimals. So I got 0.9048, I got 0.0027, and I got 0.0925. Again, you have to move the decimal point over 2 times in order to convert percents into decimals. And so now I'm going to go ahead and write out the whole equation. We have 20 times 0.9048 plus 21 times 0.0027 plus 22 times 0.0925 if you multiply them out and add them all together. Now make sure if you're plugging them into the calculator, you're using parentheses like between each of these so that it knows to multiply them and add them together after it's multiplied. That would be my only hint for calculator usage. And when you multiply all of these out and you add them together, you should get 20.188 or somewhere around there if you rounded differently. Does this answer make sense if you look at the percent abundance? And you should answer yes. It should be closer to 20 because neon 20 is a 90.48% abundant, so it's mostly neon 20, so it makes sense that it's close to 20. Question number 5, we already went over, but I will quickly go ahead and do it on the worksheet so that you'll have it as part of the video. We have 2 isotopes of calcium, 40 and 46, and we have the average atomic mass of calcium from the periodic table, and it wants us to go backwards and calculate the percent abundance. So this is really an understanding problem. Can you apply your understanding to something completely different? And so we start with our calcium from the periodic table. We have 40.078, and you're going to set that equal to we have one isotope that's at 40, but we don't know the abundance, so that's going to be X. We have a second isotope that at 46, but we don't know that abundance either, so that's our second unknown, which is Y. Now you have to understand that if you add the relative abundances, X plus Y, together, they should equal 100% or they should equal 1. And so if we solve for X, so we can use the substitution method, we have X equals 1 minus Y. So now what we're going to do is we're going to plug in 1 minus Y for X, and we should be able to solve that. 40.078 equals 40 times 1 minus Y plus 46Y. I'm going to skip some of the math steps because I'm going to assume that you know how to do this, but I will go ahead and distribute this 40 minus 40Y plus 46Y. You're going to combine like terms, so it's going to become 6Y. You'll subtract the 40 over, and you'll end up getting 0.78 equals 6Y. You divide by 6, divide by 6. You're going to get Y equals 0.013 and X equals 0.987. But you have to go back to the question, and it says the percent abundance is what it wants. Okay, and so this is not the percent abundance, it's going to be the relative abundance. You have to convert these into percentages. So what you're going to do is multiply those by 100, and you should get calcium 40 is going to be 1.3% abundance, and calcium 46, oops, I messed up. That's opposite. So it should be 98.7%, and then calcium 46, which would be Y, is 1.3%. So don't make that mistake that I did. Make sure that you realize what your X's and your Y's are. Now the reason that I was able to catch that mistake was because if you look at your original atomic mass, it's 40.078, so your calcium 40 should be the most abundant type. All right, so don't make the mistake I did. Make sure that you realize what your X's and your Y's are standing for. All right, so now if we go down to Model 2, Model 2 is actually giving us mass spec pictures, and it's asking us to kind of analyze those. So question number 6, how many isotopes of lithium exist? So I know that lithium has 2 isotopes, and the reason I know that is because we have 2 peaks in the picture. Question 7, what masses are present on the graph for the following? So the mass of the most abundant isotope. So the mass of the most abundant is going to be 7. I know this because this is the highest peak. All right, so the mass of the most abundant isotope is 7. The mass of the least abundant isotope is going to be 6. Label each peak with the nuclide symbol for each isotope. So that's just going to be Li6 and Li7. And then question 9, without performing any calculations, predict the approximate atomic mass for lithium. Explain the basis of your prediction. So lithium is going to be somewhere between 6 and 7, and it's going to be closer to 7. Okay, and so why am I saying that? Well, if you look, the relative abundance and the relative intensity, lithium 7, there's a much higher peak there. So it's going to be closer to 7 than it is going to be to 6, just simply based on it's going to be more common. Now calculate the average atomic mass of the element from the mass spectrum data. The height of each peak is the relative intensity, not the percent abundance. So make sure that you're reading your axes so that you know what you're given. You're first going to need to calculate the percent abundance and then the average atomic mass. And so it kind of walks you through that. So the relative intensity of each peak. So peak 1 I'm going to say is the short peak, and the relative intensity is going to be 8. And peak 2, the relative intensity is 100. And so now we're going to take those numbers, and the total is going to be, we're going to add them all up. So the total is going to be 108, and that's what we're going to use to calculate the percent of the intensity. So for peak 1, what you're going to do is you're going to go 8 divided by 108 times 100, and you should get 7.4%. And so for peak 2, you're going to go 100 divided by 108, multiply it by 100 to change it into a percent, and you should get 92.6%. And so now part D is asking us, we just determined the percent abundance of each isotope, and now it wants us to calculate the average atomic mass. So for this one, let's go lithium 6. We have a mass of 6, a percent abundance of 7.4, and for lithium 7, we have a mass of 7 and a percent abundance of 92.6. We have all the information we need to calculate it, so we're going to go 6 times 0.074 plus 7 times 0.926. If we calculate all of this out, we have 6.926. 6.926. Does that make sense with our data? And the answer would be yes. We predicted that it was going to be between 6 and 7. We predicted that it should be closer to 7 than it should be to 6, which is what we get. Now, question 11 is asking you to kind of think back and maybe do a little bit of research if you don't remember what Dalton's early model of the atom was. And so basically, Dalton's early model of the atom was that an atom is a very tiny, indivisible, indestructible, and unchangeable solid sphere. And now we know that that's not quite true, but it gave us a really early theory about the atom, and it helped us build the periodic table. But mass spec actually contradicts this, and because for the simple reason that atoms of the same element can have different masses. If his early model was true, all atoms of the same element would be exactly the same and have the exact same masses. And so that's what you would kind of say something about in part A, is something about atoms having different masses. So atoms having different masses, even though they are the same element. Okay, that's not a very graceful answer, but something to do with that would be what you would answer for part A. Part B, how does data from mass spectrometry demonstrate direct evidence of different isotopes of the same element? Again, the peaks. We have different amount of peaks. So the peaks are what explain this. And then question 12 is giving us a picture of a mass spectrum, and it's asking us to figure out what element it is. So basically what we're going to do is we're going to calculate the average atomic mass, look at the periodic table, and see which element is going to be closest to that. And so this relative intensity, I'm going to say it's at about 60, and I'm going to say this one's at about 100. They're pretty close to that. Make sure that you don't use 50 for that 185 because it's a little bit over 50. And so when you do the percent abundance, because remember this is relative intensity, so we need to change that to percent abundance. So what you would do is you would just do 60 divided by 160, multiply that by 100, and you should get this percent abundance at about 37.5%. And if we do the same thing here, 100 divided by 160 times 100, we're going to get something at like 62.5% abundance. And so now what we are going to do is 185, because that's the mass down here, and 187. So 185 times 0.375 plus 187 times 0.625. We add them all up, and you're going to get 186.25. If you look at your periodic table, that's going to be very close to Re or rhenium. And that would be how you would do that.